Okay, well, mechanical energy is potential energy plus kinetic energy. That's equal to your total energy, total mechanical energy. If there's no dissipation, which is the case if all your forces are conservative, and that is, of course, the case in an ideal electric circuit with no resistance. If all your forces are conservative, then potential plus kinetic energy is constant. That's the ideal pendulum. It just keeps going. It never dissipates energy because we have the ideal situation where there's no dissipation. In reality, of course, the amplitude of the pendulum, unless you drive it a little bit, unless you add a little energy every once in a while, is going to decrease and approach zero. Okay. In any case, that's our situation, and hopefully that's something that you got pretty solidly into your head back in October, in the early part, the latter half of the first part of the first semester maybe. Okay, in an LC circuit with no resistance, the total energy is just the energy on the capacitor plus the energy on the inductor. And of course we just derived those expressions. Q squared over 2C, that's a potential energy. Capacitor's holding a potential energy. The 1/2 Li squared, if this is a potential energy due to Q, then this is like a kinetic energy due to the change in Q, the rate of change of Q. In the same sense, or in an analogous sense to the way the kinetic energy is due to the rate of change of position. Potential energy is energy due to position. Kinetic energy is energy due to rate of change of position. Here, this potential energy is energy due to charge and stored charge, and this is energy due to the rate of change of the stored charge. Okay? Time rate of change of stored charge. This is analogous to kinetic energy. It's 1/2 Li squared. Kinetic energy is 1/2 mv squared, suggesting that L acts like the mass and I acts like a velocity. Now, I just referred to kinetic energy as depending on the rate of change of position, just like current is the energy in the inductor depends on the rate of change of charge. So there's a strong analogy between the two, and the analogy continues to when you look at the differential equations, which we're going to do in a minute. Okay, now I'll note then that in a mechanical system, you know that you have mx double prime plus kx. Now this is a mechanical system with a linear restoring force and no other forces, no dissipative forces, no other forces. So I say a mechanical system, well, this is a simple harmonic oscillator. The simple harmonic oscillator. So it's not as general as I might have accidentally implied, but that's it. And we're familiar with this. We know how this works out. We know how to solve that equation. Okay? It's a mechanical system with no drag, no drive, meaning we're not driving the system with anything, so the net force is zero. Okay? Now, the net force is actually equal to the restoring force, which is negative kx, and there's no other force involved, so that when we sum these, we get zero. And I say a linear restoring force because, of course, that's a condition that gives you simple harmonic motion, simple harmonic oscillator. Okay, down here the equation is LQ double prime plus 1 over CQ equals 0. As we know, this is a voltage drop across inductance. This is a voltage drop across the capacitor. This is an LC circuit with no resistance and no drive. We have equal to 0. It's a homogeneous differential equation. For those of you, the majority are in that course. No driving force, no driving voltage, no driving source. Okay. We solve either of these equations very easily. We let X or Q, depending, equal AE to the RT, and we just do what follows, and everybody's pretty good with that. The equations are identical in form. You have a multiple of the second derivative plus a multiple of the function you're taking the derivatives with, the position function in this case, or the charge function in this case, equals 0. Same equation with different letters. Okay, well, we're going to look at how we solve that equation, but it's fairly straightforward. And remember the analogy between mechanical systems and, mechanical system with no dissipation and a linear restoring force and an LC circuit. Okay, this analogy between potential and kinetic energy and so forth.